Hi, my name is Lucky Owefi, and this is my Lab 2 for Physics 2212 covering lines of charge. The purpose of this lab is to compare how the point charge model holds up against a model that more accurately represents real life using lines of charge to more accurately represent charges distributed across the surface of the piece of tape. This will involve breaking down or otherwise integrating over the surface into segments of 30. Fundamental concepts involved include Newton's second law, Coulomb's law, superposition, and the force of the electric field as described by the equation on the bottom right. For a preview of the results, a charge of 5.97 times 10 to the negative eighth was required to hold the charges above each other. This is as compared to the charge of 4.4 times 10 to the negative eighth that was calculated in the last lab when the tapes were represented as point charges. The difference in forces was approximately about 32% in the end, but as you can see for the top charge, it was 1.95 times 10 to the negative third newtons required to hold up the charge versus about 1.06 times 10 to the negative third that was generated from the point charge model. Some key assumptions were required for this experiment to work. Firstly, each tape was modeled as a collection of subcharges where for this experiment there were 30 subcharges used. The principle of superposition was also required for this estimation. Additionally, air resistance is considered to be negligible, and not only that, each portion of the tape is also assumed to have equal amount of charge. The code was created using GlowScript, and here are some of the conditions that were used. A tape mass of about 0.002 grams. The tape length was about 0.2 meters. The distance between the two charges, or the two tapes once they were stable, was about 9.95 centimeters. The force of gravity was calculated to be mass times acceleration here on Earth, and the force of the electric field was equal to the force of gravity since there is no acceleration observed at the tape at this time. Here are some snippets of the code that was used to generate this experimental model. The topmost image is some of the constants that were used, for example, the distance being 0.0995 grams. Then you have the definition of the electric field on the bottom and some of the code that was used to create the visual effects for the electric field. Here are more pieces of the code. The top one shows the integration of the electric field across the multiple points, and the bottom one is also just the integration across the 30 segments for the actual force exhibited on both of the tapes. So as for the results and the observations, the top image shows the charge of 4.4 from the generated from the last lab and how the forces contributed by both from gravity and the electric field are insufficient to keep the tape afloat on each other in this model. On the bottom is the actual amount of force that is needed to keep both of the charges on top of each other floating with no acceleration. The charge for that was about 5.97 times 10 to the negative eighth, and like I said earlier, the required force equated about 1.9 times 10 to the negative third. This shows that the point charge model was not an accurate representation and that the line charge model more accurately represents. So further discussion. In the previous lab, we assumed that the charge was positioned at a single point. This model also distributes the charge evenly along the tape, and the point charge model underestimated the charge that was required. The line charge model more aligns with the experimental observations and produced forces that do actually balance each other out equally. If modeled as a point charge, a Q of 5.97 times 10 to the negative eighth would be needed as opposed to the previously calculated charge of 4.4 times 10 to the negative eighth. This is about a 32% difference in charge that was observed, which is significant enough to say that the previous model was not an accurate representation. The charges differ because the point charge underestimated the required charge. When modeled as a line, the charges spread out in 30 different segments produces a much larger force that actually equates out to the force of gravity. The line model was a much more accurate and produced a far more stronger force. In conclusion, the line charge model provides a more accurate estimate of charge. Additionally, charge distribution plays a much more important role in force calculations here, and therefore moving forward in the class is why we are using these breaking down integrals of force on a surface. Future improvements might including air resistance and refining the definition or charge distribution assumptions. Thank you.